The 4 acceleration a mu is defined as the rate of change of 4 velocity u. If I go to the rest frame of the particle, how can I consider that rest frame as an inertial frame? So to resolve that problem, you have to actually think this accelerating particle or the frame of the particle uh, in terms of a series of inertial frame, each moving with a different velocity. So you can think the rest frame of the particle for a say small time interval delta t, within which the velocity doesn't change much. So you can roughly treat the velocity of the particle to be constant within that short time interval and regard the rest frame of the particle to be an inertial frame. So if you do that, you have to actually consider a number of such frames in time. So for each interval delta t, you may have to consider one inertial frame attached to the particle. So by doing that, you can actually, still remain within the realm of relativity, special relativity. You don't have to think about non-inertial frames. Okay, so first of all, how to define the acceleration? We all know about 3 acceleration, right? How the 3 acceleration of particles defined, right? So rate of change of velocity, time rate of change, and you can define it. I mean, just we define as we defined velocity, 3 velocity in Newtonian mechanics. So the 4 acceleration is usually denoted as where is that? Just a minute. Usually it is denoted as a mu. Of course, you can use a different symbol, but I will not suggest to use any other symbol because sometimes that may be confusing. So a mu, acceleration 4 vector, and this is defined as the rate of change of 4 velocity. Of course, acceleration is the change of velocity. The rate of change of 4 velocity, u mu, that we have already learned. And of course, this rate of change has to be with respect to the proper time, not the time that we usual times, the proper time, that is the time in the rest frame of the particle. So that is the definition of the 4 acceleration. The 4 acceleration a mu is defined as the rate of change of 4 velocity u mu with respect to the proper time. Now, if you consider that kind of definition, of course, you can see that because the 4 velocity is already a 4 vector, right, which obeys Lorentz transformation. Now you are defining another 4 vector a mu, which is defined as equal to d u mu for velocity d tau. Now d tau is a Lorentz invariant, right, proper time, so that is not going to change, and u mu is the 4 velocity. So of course this will obey Lorentz transformation. And I will explain the geometrical meaning of this, but let us first write down the mathematical expression first, and then we will discuss about its geometrical meaning. So if I write down a mu, hello, okay, let me just go back. Can you see the whiteboard?
Yes,
hello. Okay, fine. So a mu, the 4 acceleration is defined as that derivative of the 4 velocity with respect to the proper time. And you can simply write down this because we know the expression for u mu, right? What is u mu? If you remember gamma u and c ux uy uz. So first of all, let me write down d u mu. So I'm taking derivative with respect to normal time, and dt d tau. I can always write that because we know that dt d tau, and that is, you can write this to be gamma. So this is basically gamma u. Remember this subscript u, because otherwise, gamma can be, it's a Lorentz factor associated with the particular velocity. Here we are talking about the velocity of the particle. U is the velocity of the particle, not the velocity of any frame. That you should remember, right? So dt d tau is gamma u. U is the velocity of the particle. So this is the Lorentz factor associated with the velocity of the particle, and the rest is du mu. So there is not much space here. So du mu d t, right? And what is u mu? If you remember, the 4 velocity u mu was gamma u, then the first component is gamma u c. So I have taken gamma u outside this, and then you have this ux uy uz. I am writing them in a combined manner. So u is the 3 velocity of the particle. Now We just have to take a simple derivative of this forward velocity with respect to time. So that is straightforward. Let us do that. So a mu will be equal to gamma u, this gamma u outside there. No, this gamma u, sorry, this gamma u, because this has to be taken, if we take the derivative of this gamma u, right? So gamma u, and then we are taking time derivative. The first component is gamma u dot times c, comma, and then we have gamma u. So we have to take derivative separately, gamma u dot u plus gamma u du dt. Now you see, because of this this gamma u dot term, the things becomes a little bit complicated. It is not as simple as 3 acceleration. This gamma u dot, because we have to calculate gamma u dot. Okay, let us simplify this first. So this is basically the time component, gamma u dot times u square du dt. Anyway, du dt is nothing but 3 acceleration. I can write a, small a. Du dt is 3 acceleration, right? And u is the 3 velocity, that you should remember. Now, because of this gamma u dot term, things the components becomes a little bit complicated and a little bit hard to handle. Let us first calculate gamma u. What is gamma u dot? Because you know gamma u. What is gamma u? 1 over square root of 1 minus u square by c square. This is gamma u. So it is straightforward to calculate gamma u dot. Take a time derivative. That means minus of half 1 over 1 minus u square by c square whole to the power 3 half, and then inside bracket minus of twice u by c square, and then dot, because it's a vector, so du dt, or simple acceleration vector a, right? This is, so minus 2 gets cancelled, minus and minus becomes plus, right? So this is nothing but gamma u cube, right? So I can write this to be equal to gamma u cube. This is gamma, because 1 over square root of 1 minus u square by c square is gamma u. So this first term is nothing but gamma u cube. And then you have u dot, u is the 3 velocity, dot this term over here, this is 3 acceleration, right? So u dot a is the 3 acceleration. Okay, let us put that inside a bracket, and then c square. This is gamma u dot. Now, if I multiply this gamma u dot with gamma u, you can see this will become gamma u to the power 4, right? There is a c here and there is c square here. So once u will be cancelled. So let us write down the expression for a mu first. So a mu, okay, a mu, okay, maybe I can go to the next page. New page. হ্যাঁ বলো। ওকে,
এক্সপ্রেশনটা একবার বলতে পারবে, ওটা কি করে হলো ওটা?
কোনটা which one?
এ মিউ সেকেন্ড এক্সপ্রেশনটা, গামা ইউ থার্ড ব্র্যাকেট।
Wait, understand. Eta. This line. Which line are you talking about?
Second line, a mu equals to gamma u, third bracket gamma u c, comma gamma
Right.
u dot e.
Okay. So look at this first line. Right? So this a mu is defined to be the proper time derivative of the forward velocity, right? So that gives us gamma u times the normal time derivative of the forward velocity. So gamma u term is there. So this gamma u comes from here, right? This gamma u is this gamma u, and then take a derivative of this thing, right? Du mu dt. So du mu is one. So I'm taking the derivative of each component. So the time component, take gamma u dot. This one is gamma u dot. C is a constant that is left here, and then we have the special component, which is, you can write ux, uy, uz if you like. This is gamma u times u. U is the 3 velocity. So there are 2 variables here. Both can be. I mean, you can take a differentiation of both the terms with respect to time, because gamma u, you see, that's a function of velocity u, right? So that, which is again a function of time. So gamma u. So gamma, that's why I take derivative of the first term first, gamma u dot, and then u is and then plus gamma u kept, and then take derivative of u, which is nothing but the 3 acceleration. Is that 0 in the rest frame? So that it will be 0, and what will be gamma? Because velocity is 0, gamma u square will be 1, because gamma u is 1, and this is the instantaneous acceleration at that moment, right? At that small interval delta t, right, within which the velocity doesn't change at all, right? So this is the 4 acceleration in the rest frame. 4 acceleration in the rest frame. Now, if I ask you, I mean, how do the components changes from one to other? That is trivial, right? You can easily, because this will follow Lorentz transformation, so you don't need to bother about how the components will in one frame will. That's defined by, so this is one frame. Suppose, imagine this is a one frame, say x, y, z, x, y, and z. Let us call this frame S, and then another inertial frame, say let us call that x prime, y prime, and z prime. The axes are different, O prime. Let us call this frame S, let us call this frame S prime, and suppose this frame is moving along x-axis with velocity, say v, and we have a particle, right? A particle which has a 4 acceleration, say a mu, in this frame, right? In this frame, S frame, and we want to calculate the component of the 4 acceleration in this frame. So since we know that it's a 4 vector, so we don't need to worry at all, because then we know that it follows the Lorentz transformation. A0 prime will be gamma what? How do I transform the time component? A0 prime equal to gamma. Anyone?
A0 minus
right, gamma into A0 minus
Beta.
beta. Anything else? A1. Now what this gamma and beta, gamma subscript ki hobe ekhane?
Sir, gamma v.
Gamma v, right, good. And what is the subscript for beta here?
Beta v also.
Good. So remember this, because you may get, I mean, sometime, I mean, if you don't remember that, ekhane gamma u is kore asche, ekhane again gamma is gamma v, because you are transforming the 4 vector between 2 inertial frame. That gamma u is the velocity of this Lorentz factor corresponding to the velocity of the particle. So that is gamma u, right? And similarly, A1 prime will be gamma v in a simple manner. A1 beta v A0, and A2 prime will be A2, A3 prime will be A3, right? So here I have taken a simple transformation. Of course, you can take any arbitrary Lorentz transformation and write the components accordingly. So they follow Lorentz transformation. Fine, but let us first understand the geometrical meaning of this 4 acceleration, because we have not yet visualized how it looks like, because we have a, I mean, intuitive feeling of what 3 acceleration is. But okay, we are writing some mathematical form, but we have to visualize it, right? To understand that, okay, let me just calculate another thing which may clarify its physical meaning. Okay, so let me just go to the next page, new page after. Okay, so what is 4 velocity? Okay, let me just 4 velocity. Okay, geometrical meaning of 4 velocity, or so what is 4 velocity? If I ask you what is 4 velocity, so we have space-time diagram. I told you that you cannot draw all the 3 space component and the time component. Here I am drawing only the one time axis and say one spatial axis, right? So the trajectory of any particle in the space-time diagram is called world line. The way the particle moves in the space-time is called a world line. So you can consider any particle, right? And when a particle moves with constant velocity, any idea how the world line should look like? Suppose a particle is at rest. How the world line should look like? A particle sitting at a fixed location in one inertial frame. How the world line should look like?
Parallel to CT axis.
Right, parallel to the CT axis, right? And a particle which is moving with uniform speed, uniform velocity, how that should look like?
Straight line.
Straight line, right? Good. Straight line. It should move in a straight line, right? Straight line. That's the important thing. So then if I have an arbitrary word line, right? So something like this, right? Arbitrary word line. Now, clearly you can see that's not a straight line, it's a curved line. That means it is not moving with uniform velocity. It has some acceleration. The moment it has an acceleration, it will bend, right? And how to visualize velocity and acceleration. So velocity, see the 4 velocity, not the 3 velocity. I'm talking about the 4 velocity. The 4 velocity is basically, if you consider any space-time point, so I mean, you take x, y, z, and ct. A particular point is basically an event in the space-time diagram, and at that particular space-time event, I mean space-time coordinates, the particle is suppose here. And if I ask you what is the 4 velocity, how do I visualize the 4 velocity in this space-time diagram? So that is basically a tangent to the word line, right? Like when we talk about velocity, we have a particle with a well-defined trajectory, and we take a tangent to that. Here, it is not a simple trajectory; it's a space-time. It's a trajectory in the space-time diagram, which is called word line, and u mu, the 4 velocity, is basically a tangent to the world line at a particular event here, say x, y, z, and ct. That's the 4 velocity, right? But how do I visualize acceleration? For example, if I ask you that the two examples that I gave earlier, right? So particle suppose moving along the x-axis, right? So of course you will say that okay, velocity is along the x-axis, right? And also the acceleration is along the x-axis. So you have only x component of velocity, so I should not write a vector here then, and only the x component of acceleration, because the particle is moving along x-axis, right? And when I told you that the particle is moving in a circle, you will clearly see that the velocity and acceleration are perpendicular. The velocity is tangential, acceleration is along this direction. But how do I visualize acceleration in the space-time diagram? This is the 4 velocity, right? That we know that that's a tangent to the word line. Now, to understand that, we have to actually calculate the dot product between velocity and acceleration. So what is 4 velocity? How do we, what is the expression for 4 velocity? U mu is gamma u times, I mean, c and u. Space component, time component, gamma u c, and space component is gamma u u. I mean, ux, uy, uz, if you write them explicitly. And once I write the contravariant component, covariant components are simply gamma u c minus of u. And what is the 4 acceleration? I wrote it a couple of minutes back, a mu. So I am writing the simpler expression gamma u dot c, that is easy to remember, gamma u dot u gamma u square a du dt a, right? This is a mu. Now if I ask you to calculate this, say a mu u mu, you can easily calculate by using these expressions. So what is that? You can take a dot product of this and that. So this will be gamma u square gamma u dot c square minus gamma u cube into a dot u whole square minus gamma u square gamma u dot into u square. If I take this common, gamma u square gamma u dot c square minus u square minus gamma u cube, right? Gamma u square gamma u cube a dot u, the middle term. So I am taking common from this and this, okay. Gamma u a dot u, okay, right? This is not square, this is not a square, this is wrong, right, is equal to then gamma u square gamma u dot c square, commonly লিখি হবে 1 minus gamma u cube a dot u by c. Saying you that the four velocity and four acceleration are orthogonal to each other at each and every point of the world line, which is a bit counterintuitive. Why? Because you see, in a three-dimensional world, when the particle is moving along a straight line, the velocity and acceleration are collinear, right? It is, I mean, they cannot be orthogonal, right? Of course, when it is moving in a circle with some acceleration. See, here also you can have acceleration, here also you can have acceleration. But in this case, they are collinear, here they are orthogonal. But in case of a four-dimensional space-time, that is when the particle is moving along the world line, the four velocity and four acceleration, they are always. Do you visualize that? As I told you, that a particle which is a constant velocity moves in a straight line. The moment the particle bends, suppose this is going in, right? It bends somewhere. That means the velocity was tangential to the world line. Here also it is tangential to the world line. The moment it bends, so it quantifies the curvature of the world line as well as the direction of the. I mean, you can see that this direction is towards bends. Okay, now suppose the world line moves like this and goes like this. Again, here the four velocity is tangential, right? The four acceleration will act along the curvature, right? The magnitude will depend on the curvature. And how large the acceleration is, that will depend on the curvature of the world line. So, world, you have to visualize velocity, the four velocity, as a tangent to the world line at a particular event, and the four vector, which is orthogonal to the four velocity. Now you see, there is no way you can visualize a four-dimensional geometric space-time, right? Space-time, one space, one time. That's why I can talk so much, right? Otherwise, I mean, once I go to 3 plus 1, everything will be blank. It's very difficult. So I mean, it's just an analogy which makes things clear that what is the physical meaning of this quantity for acceleration. Once you understand the definition, you should be able to apply this. So I usually again suggest you to try a couple of problems. I'm giving you two problems today, right? You can do it yourself. How much time we have? Okay, another 10 minutes, so you can complete within that. Okay, so I'm giving you two problems, very simple problem, and these problems I have already given in some exam, and you can see that these problems, they're very easy to formulate. Anybody can formulate such problem. You can also formulate such problems. Okay, so let me just give you two problems to solve. Say problem 1. Okay, problem 1. This is a very simple problem. Suppose I give you a particle. Okay, it's a particle. So I'm specifying the coordinates of the particle. Okay, that's a very simple thing. So suppose the x are specified by this functions. So xt, x is a function of time, given as at plus sine, say omega t. That's a function, and then again a yt equal to say b cos omega, and say zt equal to 0. Okay, so these are the position coordinates of the particle, right? Velocity of the particle, say u mu, and you have to calculate the 4 acceleration. This is a, this is a trivial exercise, but of course you have to be careful about calculating things. 4 velocity is straightforward because you know what is 4 velocity. Is simply gamma u times c comma u, right? So you just have to take derivative. You have to, because the component z, so you have to take derivative of them in order to write down the 3 special components of the 3 velocity, and of course gamma u, another factor. Calculate u, magnitude of u in terms of a, b, and omega, that you can do. And also I a mu, right? A mu is what? A mu is again gamma u to the power 4 u dot a by c. What is u? What is 3 acceleration? Then take the dot product and then simplify that. So this is a simple exercise, but of course you have to do square a plus gamma u to the power 4 u dot a by c square times, right? So I'm leaving this as a homework, because I hope once xyz is given, all of you can take these functional forms in order to calculate 4 velocity and 4 acceleration. Okay, okay. Now suppose moving, say, on a plane. Okay, of course you can move in any other dimension. It's moving on a plane with relativistic velocity of the particle. Suppose the particle is moving on a plane, and the instantaneous velocity, suppose particle is moving in a plane, and suppose this is a, and at this particular point the instantaneous velocity of the particle is, say, given as a u equal to 0.99 c, right? At this point, say a, right? And clearly you can see the velocity and acceleration need not be parallel, or it can have other components as well. It's 2 dimension, so x and y are there, because, and there, since there is a curvature of the trajectory here, right? Given is this way, acceleration a is given, a equal to, say, it has both x component and, say, y component, right? A y cap particle at this point, and this is the velocity magnitude of the velocity. Of course, if you want to know what is the direction, this is along x cap. Okay. At point it will be having different velocity. Now if someone asks you to what is the 4 acceleration, a mu, you have to calculate a mu. Now my suggestion will be, read, put the values blindly in the formula. Of course you will end up into wrong result, right? Because what, in my experience, these are simple things, but think about the problem clearly. The calculation obviously wrong. So you can see that this kind of problem, so I will not suggest you to follow any particular books. There are no such books which discusses these problems, right? Okay, because I can formulate 10 problems, because you can see if I change the functional form, this problem will be different. Or if I take it, suppose I take a pendulum here. Okay, so suppose this is x-axis, y-axis, this is y-axis. I have a pendulum, okay, moving, right? If I ask you what is the 4 acceleration of the pendulum here, calculate it. You can formulate many such problems. The main thing is you have to understand the underlying idea, and that is what I emphasize most in my course. Focus on, how much calculation you can do. Calculation is definitely an important thing which you must be able to do. Underlying idea clearly. Once you understand the idea, you can you can learn the other things yourself. There is no need of a teacher. So the basic concept clearly, and then be able to apply those. So okay, so I have just given you 2 examples. Think about other problems, or you can search different books. So I do not have any suggestion, because I told you that for the Jackson's book and the exercise of Jackson's book, where there are different types of problem, but of course not all kinds of problem that I am discussing in the classes. So I stop here, and if you have any questions regarding the discussion that you have carried out today, please ask. Any question? Okay. No question. Can you hear me?
হ্যাঁ স্যার শোনা যাচ্ছে।
ওকে ওকে, ঠিক আছে ঠিক আছে, তাহলে আমরা ফোর প্ল্যানটা বলি। আমি ধরো আমাদের যেটা ইনিশিয়াল যে প্রেসারটা ছিল সেটা এখন নেই, কারণ যেহেতু যদি আরো জানুয়ারি ফেব্রুয়ারি, তো আই এম নট শিওর, তাহলে অনেকটাই সময় আছে। আমরা আমরা আমি যেটা ভাবছিলাম যে এগুলো হয়তো মেনশন করে চলে যাবো our time and discuss these things. So relativity আমি ডিটেলসই পড়াচ্ছি, যেমন আমি স্কিপ করছি না বেশি কিছু। তো ফোর অ্যাক্সিলারেশন হয়ে গেল। তো ন্যাচারালি জাস্ট রিলেটিভিটি পড়ছি না, আমাদের একটা গোল আছে। সেই গোলটা কি? গোলটা হচ্ছে আমরা ইলেকট্রোডাইনামিক্স যা কিছু পড়েছিলাম, মানে ইলেকট্রোস্ট্যাটিক্স, ম্যাগনেটোস্ট্যাটিক্স বা মানে 4 ডাইমেনশনাল স্পেস টাইমে বুঝতে চাই, ওগুলোকে রিফর্মুলেট করতে চাই। তো সেটা করতে গেলে ন্যাচারালি আমাদেরকে বুঝতে হবে যে ইলেকট্রিক বুঝতে গেলে তখন আবার সেটা রিলেটিভিটি ইজ মাস্ট। উইদাউট রিলেটিভিটি ইউ ক্যানট আন্ডারস্ট্যান্ড দ্য মিনিং অফ ম্যাগনেটিক ফিল্ড আর ইলেকট্রিক ফিল্ড। And then we see in electrodynamics we have another equation which is important equation, which is Lorentz force equation, right? That gives you what is the force acting on a charge. And you see how do we deal with force? See, in Galilean transformation, if you go from one frame to other frame, force remains same, but that is not the case in case of you have today I have discussed about four acceleration. So naturally in the next thing that will come up will the four force, right? Mass, time, acceleration is the force. How the force transform between different inertial frames. So once we understand how force transform, then we will be able to understand how electric field and magnetic field transform, and that will electric field and magnetic fields are actually what are their real nature. So that is our goal of the whole discussion, right? So why we are discussing that. And when I talk about force here, we'll be talking about only the electromagnetic force, not the other kind of force, because no force, right? It's not in non-inertial frame when you deal with gravity, for example. So in that case as well, you have a equation, right? That is the geodesic equation. Equation actually gives you in that case, I mean, if I ask you what is the force acceleration of a particle, right? In that case, up force in relativity. So that's a separate story. I am not going into that. So our entire discussion will be focused only on the magnetic field. So that I will discuss in the next class. Okay, thank you.